Welcome to the presentation of Physical Route Manager. PRM is a Globema-made add-on to the GE Smallworld Network Inventory product suite. This presentation will show how you can benefit from using PRM in your company. It will also discuss which problems PRM solves. It will introduce you to PRM basic features and also to some of its more advanced functions. Let's take a look at common problems that PNI users struggle with. Complex fiber network is very difficult to maintain. In order to create a path in fiber network, users have to visit each individual splice and manipulate connectivity inside them. During this manual work, they usually make a number of mistakes, which then are difficult to fix as it again requires manual changes of fiber connectivity. For the similar reason, handling network outages is pretty complex. There is not enough information in standard PNI on fiber designation, and this is the critical data necessary in this process. PNI does not provide a convenient tool to generate documentation for network build or network reconfiguration. And last but not least, PNI has to provide accurate and up-to-date information about available network capacity, which cannot be delivered without proper fiber designation tracking. From the process's point of view, PRM supports network design by allowing users to create and plan routes in fiber network by hand or automatically. Service fulfillment by delivering the environment in which business-to-business services can be designed and documented. Network build by providing resource reservation mechanisms and convenient documentation for field workers. And finally, service assurance by reporting accurate and up-to-date information about network occupancy as well as detailed information about each service passing on any network resource. Here you can see how PRM fits in the whole Smallworld network inventory landscape. It seamlessly integrates with both PNI fiber data models, Job and Design Management, Logical Network Inventory, and Optical Network Atlas, another PNI add-on by Globema. Physical Route Manager allows users to group any number of physical resources into an easily accessible and manageable entity called route. Route consists of consecutive elements such as fibers, ports, and splices that comprises a connection between two locations. With PRM routes, you can model how your fibers and ports are utilized, whether it is for company's internal data transmission, digital services for customers, fiber lease, or wavelength lease. Main features of PRM are rich and intuitive user interface, assisted manual or automated routing, highly optimized network tracing on fiber level, and routes lifecycle supports. PRM extends physical network inventory with a lot of new features. With Physical Route Manager, users are able to store information about fiber designation using PRM routes. Users can create connectivity with respect to the actual transmission entity. Tracing information for each element is provided instantly while routing. Most of route design can be automated using dedicated routing algorithms. Resources can be reserved using PRM, and finally, PRM delivers quickly convenient data about current network occupancy. With this feature, it allows to manage network outages better and supports network build team with up-to-date information about available network capacity. Now, let's take a look at Physical Route Manager in action. PRM is a separate application in PNI environment. You can launch it from Application Manager or from PNI Tools menu. It can be run together with PNI or together with LNI, and does not require additional Smallworld license. PRM GUI has been optimized for network routing and routes creation. It has 5 main application areas. On the upper left, route details area. Here, above the map, construction area. Route candidates panel in the bottom left. In the center, the usual map control. And here in the bottom right, other PNI tools are available, such as viewer, object control, connectivity, and of course, project pane. I would like to introduce you now to these 2 main concepts of PRM. PRM introduces route object, which is point-to-point connection in a fiber network. 1, 2, or more fibers can be traced in parallel. The second object is an issue, which is one of many possible variants of a route, which can span differently throughout time. Let's go back to live demo, in which I will show you what kind of information can be retrieved having some PRM data already in database. First, take a look at one already existing route. Its attributes show how many parallel fibers were used for construction, what is the type of the route, and there are also some derived fields whose values have been taken from issues. We will discuss some of route parameters later on. Here in Issues tab, you can see all issues defined for this route. Here we can see only one of it, one issue. For this issue, we can see description of all elements which have been used for construction of this issue. The green color says that these are some elements inside buildings, ports on shelves or on carts. Purple denotes fibers in optical cables, and blue connectivity in splices. This report list of elements can be exported to Excel file, which is a very convenient way to hand out information about route to field workers. This Excel file contains exactly the same information as here in PRM GUI. Here on the right, you can see the same issue, the same fiber path presented graphically. These are buildings which contain some ports located on shelves in bays. Here you can see shelf name and name of ports. Here you can see description of floor, room and bay in which the shelf is located. Here you can see a splice and information that these fibers 3 and 4 from this cable and 3 and 4 from this cable are connected inside. And this is how the whole route is presented to the user. Each element can be investigated and collapsed again. This right panel shows you the total length of the whole path and length of each cable section as well. Using these buttons, you can present additional information. For example, combining these two buttons present you what cables are connected to each location in the PRM and which locations are accessible through these cables. For example, this information says that from this building, if you use Ethernet feed CWDM cable, you can access all these locations, and the total distance to these locations is given right to location name. When you click one of these locations, you can see the occupancy of fibers in this cable. The blue color denotes occupied fibers, green color denotes free fibers. Using this additional information, you can quickly think of how you can manipulate, reconfigure your network in order to reach some other location in your fiber network. Each element can be obviously shown in the main map. So in this example, let's use goto command and see how this fiber path goes through our whole fiber network. These dark yellow elements here in the main map show all structures which are consumed, which carry all elements which are elements of this fiber route here, which was discussed a while ago. Now let me show you how PRM data can be extracted, can be found in PNI. PRM is integrated with PNI and provides convenient tools to get as much information as possible in PNI. Here you can see that this manhole has been selected. Each PNI element which can be occupied somehow by fiber network received additional PRM data tab in its editor. In this tab you can see all cables which are passing through this element, and for each cable you can see all its fibers with information whether this fiber is occupied or free. Occupied fibers are indicated in purple, free in green. For each occupied fiber you can see the list of all PRM routes which occupy this fiber. Here you can see two of them. Here you can see also two, and in fibers 4, 5 and 6 only one. Each object can be edited also in PNI. You can see all attributes of this route, also information about its issues with Excel report possibility, and by pressing this button, user is taken back to PRM in order to manipulate with issue elements. In this tab you can also see all devices which are reachable by all PRM issues passing this element. So it can quickly show you all bays, shelves or cards which terminate PRM routes passing through this element. It can speed up your service assurance and outage analysis process a lot. In this section of my presentation, we will focus on PRM route creation. In the following steps, I will show you step by step how to create new root in PRM and how the application assists you with this task. Please pay attention to what happens in Candidates tab and how we manipulate Construction tab and how these two panels cooperate in order to help users to create their root as effectively as possible. Take a look at this root editor. Now we will fill its mandatory attributes in order to create a new database record. After providing a name for your entity, you have to select what kind of root will it be. Out of the box with PRM, you will receive 6 predefined types. Disposed root is used to model dark fiber services, some kind of fiber lease. Measurement is an object which allow you to model fiber network measurements, and users, usually our customers, associate additional measurement results to this kind of PRM root. PON root is meant to model customer service in passive optical network, in FTTH network. Physical section is probably the most common and most useful, versatile type of root. It is used to model some kind of telecommunication transmission in fiber network. It can be, for example, the physical path of your DWDM section or physical path of your 10 gigabit Ethernet section, which is routed directly with fibers. Planned splice work is a very specialized PRM root, which is used to denote change of splicing in one or more splices. Using this PRM root, you can create some report for your field workers in order to show them how connectivity has to be changed in several manholes. WDM base root is some technical entity which allows to model to insert into database the whole multiplexation section for your passive CWDM network, because usually the WDM has to be modeled in some logical network inventory, but passive WDM networks can be very conveniently modeled with PRM, and WDM base root is used to indicate that given fibers are in fact a multiplexation section between two multiplexers. So this is some technical type. We will not mention it later in our presentation. So for our purposes, we will select physical section. We will route 2 fibers, and that's all. If you select disposed root type, you can of course indicate which type of disposal of lease is it, whether this is disposal to third party or from third party. In PRM you can give some name of customer here. Usually when we implement PRM, this has to be integrated with some customer collection in PNI database. These attributes here are, as you can see, derived fields. They are computed automatically based on list of issues for this root. So this is enough for now. We have just inserted a new PRM route to our PNI database. So now let's create a new issue for this route which was created just before. New issue by default is in construction status. It means that this fiber path is under construction. So every manipulation with elements is possible. You can save your issue in this status and finish your work later. But if you want to change status to planned or active, you have to finish your work. So the fiber path has to be consistent. It has to be finished and cannot contain any gaps or mistakes. So now let's create the new route which goes from this building to Exeter North building. In order to start routing from this building, you have to select an element in the main map and press this arrow, which will take the selected object from map to construction tab. Now in candidates tab, which has refreshed automatically, you can see the whole RME structure of this building. So user can select optical distribution frame ports or maybe some other ports from this location, which will be added to the fiber path. So let's start with selecting optical distribution frame ports. You can see shelf names, card names and ports here. And you can see that expanding ports, here you can see that fibers are connected and you can see what is the destination object for each fiber. So system instantly traces fibers and shows what location is accessible using fiber level trace for these fibers. So let's select port 5 and port 6. As you can see, they have been automatically added to the route. So you can see fibers 5 and 6 are added here, and they travel to Exeter Sidwell location, but there fibers are not connected to any port in this location. So you have to select ports. But this is not how I wanted to trace. You can say that I made my mistake, so I will show you that PRM also supports undo and redo functionality. So if you made any mistake, you can simply press this undo arrow and we go back to the state from just before. Okay, so let's use another way of selecting elements. Now I have pressed this arrow here in order to select some fibers from cables which are attached, connected to this building. You can see that now candidates panel shows cable hierarchy. So you can see which fibers are connected, and again for each cable you can see what are target locations for each fiber. You can see that these first 12 fibers travel to Exeter Sidwell building, and these fibers finish their trace in some splice closure with Sidwell Street, SC1 name. So let's select these two fibers and look what happened. These fibers has been automatically added here, so we can continue our work by selecting this arrow and look and selecting elements from candidates pane. This green dotted line indicates that there is existing connectivity between these elements here and this element on the right. So connectivity between fibers 5 and 6 from this cable and 5 and 6 from this cable in this splice closure is already in the database. So maybe it is not worth selecting fibers in each consecutive cable. Maybe we can take advantage of connectivity which is already in database. PRM is ready for this and allows you to take advantage of existing connectivity by using these options: make one step and follow connectivity. Make one step option selects next connected element from the database. Follow connectivity tries to follow connectivity as far as possible. So let's try this option. You can see that going with fibers 5 and 6 and using existing connectivity took us directly to Exeter Sidwell location. Because these fibers were connected to some optical distribution frame here, these ports have been automatically added to physical fiber path. So you can see that these are ports S35 and S36 in the shelf with this name, and in rack with this name in room number 1 on floor number 0. So let's take a look which cables can deliver our service to Exeter North building. You can look for fibers in cables. So for example, this cable's name says that it goes to North building, so you can select some fibers from this cable. You can see that this Exeter North Park, the building which we want to reach, is a target location for these two fibers, but we can use destination hierarchy here to see every accessible location on fiber level from this building here. So by pressing this arrow and selecting destination, you can see here all possible destinations from this location. So you can reach James Owen Court, North Park University, and all these other elements using fibers from this location. So now we will select this object, and you can see we can use these two green free fibers. All elements which are presented in green are available to use, they are not occupied. All elements which are blue are occupied by some other physical route manager element, PRM route. So let's see what happened here. We have selected fibers 5 and 6. PRM thought that we want to connect these fibers exactly to this optical distribution frame. But actually we want to do it in another way. So we will tell the construction tab to disconnect these elements, and we will select some other distribution frame ports. Now we will use make one step. We will use make one step command in order to select ports which are already connected to fibers. And now we will close this gap, and you can see we have this dotted red line, which means that there is no connectivity between these ports and these ports. This means that if you want to activate this path, you have to create this connectivity. Okay, so now we will follow connectivity here, and we will reach Exeter North Park. Fibers have been automatically added here. Okay, so if we want to finish we have to tell PRM that this is the end of our routing. The same here. Okay, and now we are ready to switch our new issue to planned status. The whole work has been saved. You can see that these derived fields have been filled. We have planned status, and both ends are here presented here in root attributes. You can see that some of our elements have red dotted line here. It means, as I said before, that connectivity for these two objects does not exist. So once we activate our issue, PRM automatically will create all missing connectivity. It will disconnect objects which are connected in other way, provided that they are not occupied by any active PRM routes, and it will create connectivity to match our design in PRM. So you can see this is a very convenient way to manipulate connectivity in your fiber network, because you can design your services from the top level overview. You do not have to visit each splice in order to manipulate connectivity. You can see in each splice which fiber is occupied and which is free, and you can select fibers depending on their destination, which is given instantly while you select elements for your fiber route. And when you want to activate your route, all missing connectivity is created at one time in one transaction. Now I would like to introduce you to automatic routing in Physical Route Manager. Previously, I have shown you how to create fiber route manually. The process is partially automated because PRM presents very useful information about tracing results and can take advantage of existing connectivity, so it can be really very quick. But this process can be automated. Automatic tracing mechanism has been provided in PRM. So if you have 2 points, you can automatically find route in your fiber network. Currently there are 3 different algorithms which are responsible for finding optical path in fiber network, but this set can be extended and additional algorithms can be introduced, or existing algorithms can be extended. Auto-routing allows to provide a void list, so some locations or distribution frames will not be taken into consideration, and results show up as soon as they are found. Users do not have to wait for the whole computation to be finished. They see results as soon as they are found by automatic algorithms. All results are ordered by length, by number of locations, and what is the most important, by number of splice changes necessary to be introduced in order to create a route. So let's take a look at automatic routing in PRM. We will construct the same route in Fibre network as before by hand. But now we will do it automatically. To start auto-routing, you have to select two end locations for your route. So using these map arrows, I have added our James Owen Court building and North Park building at the both ends of PRM issue. You can see that here we have a gap between two locations, so there are no elements apart from building locations. If auto-routing is possible, you will see this little yellow lightning picture. When you click it, you will receive auto-routing window. In auto-routing window, you can provide some avoid objects which has to be avoided. You can order how to select optical distribution frames, but currently we will use default options. If you press start, looking for suitable fiber routes in optical network will start. This process can take several minutes depending on the length of route or the complexity of fiber network. We believe that even if it takes 5 or 6 minutes, it is still more convenient and quicker than manual work. As you can see, first results appear as soon as they are found. These are very similar routes found by the same algorithm of direct path, and each of them has a length of 1 kilometer and 20 meters and travels from one location to other location. No splice change is necessary because this is direct path algorithm. You can see elements here. These are elements which will be added to our route if we select this auto-routing candidate. You can see also some other candidates which are slightly longer, or maybe they visit many more splices or locations. Each candidate can be reviewed here before user selects the most convenient one. Default sorting is by number of splice changes, as it is usually the most important factor in determining which candidate is best. So let's select this one. So you can see that our manual work was rubbish because it was very, very long and traveled visited a very big number of splices and locations, and automated routing allowed us to select very straightforward path between these two locations. When we click this magic wand, the route is automatically completed. So you can see that these two locations were connected directly with two fibers in this cable. So now you have to finish your work and change status to planned as before. That's it. Let's discuss now WDM and passive optical networks. In current version, Physical Route Manager provides full support for wavelength division multiplexing devices and passive optical networks. WDM devices and passive optical network devices can have very complicated signal flow inside them. For some devices, it is pretty straightforward to guess how optical signal flows inside them, but for many others, it is very difficult to find automatically a route inside these devices. Globema introduced very useful PNI extensions to model optical devices within PNI. These extensions come together with PRM, but they are not mandatory. Let me show you how such an optical device can be modeled in PNI. Here we have a card inserted into a shelf, and this card comes with RME specialization, optical WDM. This allows us to fill these two additional tabs in card editor, optical ports and optical signal. In optical ports tab, we can define what kind of optical ports this device has. And for each port, we can define its type, its signal direction, and supported wavelengths. Here you can see a very simple multiplexer demultiplexer device. It has one receiving line port and one transmitting line port. They both support that many wavelengths, and for each channel in CWDM channel raster, you can see one receiving and one transmitting port. So for 1390 you can see these two ports, for 1410 these two, and so on. On the other tab, once you defined your optical ports, you can define how optical signal flows inside this device. Each line in this table is a one rule which says that if the signal on this wavelength enters this port, it will go out of the device with this port. So this is very straightforward information how each lambda, each optical wavelength is routed inside this optical device. The very important thing is that users will not be forced to define all these rules by hand. This PRM with these PNI extensions for optical devices comes with an algorithm to figure out most of the straightforward rules for each device. So you can see if we delete all these rules, we can figure them out automatically just using this information. But for some devices, this is not possible because some devices have some very non-trivial rules to route optical signal inside them. So then users will be able to provide these rules by hand. These optical signal flow and optical ports tab are available for RME optical devices, so optical add-drop multiplexers, demultiplexers, optical transmitters, optical receivers, attenuators and optical amplifiers, but also for devices which you can put inside a splice. Let's take a look at this device, which is located here in a manhole and inside a splice box. These devices can be viewed here in this Devices tab, which has been added on both windows in connectivity window. You can see WDM device here with the same information provided. So having these devices with this optical flow definition, we can use PRM to automatically take this information and use it while routing. Here we can see a very simple example for a service delivered over WDM. So we start our service here on Cisco router. Then we have a patch cord to optical distribution frame, and then the signal is delivered by WDM over this cable. And you can see that this service enters 1330 nanometers channel and then is delivered through multiplexing section of between these two devices and then exits on this 1330 channel port on the other side, and then it goes to the customer location and enters CPE device there. The same cable, you can use PRM data tab in this optical cable editor. The same cable, the same two fibers also are occupied by another service, CWDM. So you can see that currently we are looking at Toronto 31's object, PRM route. We can see that on the same fiber we have Well Street CWDM section. You can see that this one occupies 1350 channel. We can retrieve the same information using sheet editor by selecting this checkbox, show lambdas. Then for each fiber which carries multiplexation section, you can see all lambdas, and again they are colored to show occupied and free channels. So this one 1330 carries this service and 1350 another service called Well Street CWDM. So now let's try to route another WDM section over the same multiplexation section. So we will create a new route in the same relation, and we will use another channel, free channel between these two locations. So let's create a new CWDM section. It will be two fibers. Let's create new issue. We will select this one, the building, and again we will use our router here. Then we will go to ODF. So you can see that these ports are automatically added here to the graphical view of our PRM issue, and also here in our text box defining all issue elements. And now we will go to, not this one, to our CWDM device. So we will only select these two 1370 nanometers ports, and then we will follow connectivity, and as you can see we have automatically reached the second end of our multiplexation section, and PRM automatically added relevant respective ports on the other side of our section. So then the routing goes in normal way. We select next ports and reach our customer location, for example, for these 2 ports. Now we have to finish our work and save this issue. If we change this to planned, PRM will check whether wavelengths are consistent on the whole PRM route, PRM issue length, and save this object into database. So now you can see that on this cable, which we were looking at before, these 2 fibers are occupied by 3 PRM issues, and now LAMP 1370 nanometers wavelength is also occupied by planned physical section with this name. Okay, let's go to passive optical networks support. The concept is the same. Our optical devices extensions to PNI also allow us to model optical splitters. So here we have our example FTTH network. FTTH network is fed by optical line terminal located at the exchange building here. Passive optical network GPON signal is delivered to splitters, which are located in manholes here near customer locations. One of these splitters is located in the splice in the manhole here, but we have also one splitter located in exchange building. Let's take a look. You can see optical line terminal here, RME splitters located in the same rack, and ODF, which is connected to outgoing cables. Let's take a look at one of these splitters. It will show us that the same 2 tabs are available here. We have 1 input port and 2 output ports, and optical signal route is very straightforward. So each wavelength, each signal which will come using in-port will go out using both output ports. Let me show you how we can model our passive optical network customers with PRM. Let's take a look at this part of the network and check what we have here in this underground route segment. Let's check PRM data tab. You can see that we have only 1 cable, and in this first fiber you can see 4 active Toronto Road customers. They are all of kind passive optical network route. Let's investigate one of them. So you can see that this issue starts here in this building. It's Toronto Road 3, then goes through 2 manholes directly to Exeter Exchange. If we investigate it deeper, you can see that this customer is connected to number 3 output port in this splitter, which is located in the manhole here. Then it goes through this cable to optical distribution frame, which we have seen just before, and through this RME splitter connected directly to optical line terminal port 1. The concept is the same because splitters provide information how signal is routed inside. There is no fake artificial assumptions about how ports are named. The optical signal flow is defined directly in object editor. PRM is very convenient in using this information in automated or semi-automated routing. So let's try to connect another customer in the street, maybe customer at number 15. So we will have Toronto 15 customer. It will be passive optical network route with only one fiber. Okay, so we will start here at this building and we have to select starting point. All these buildings are equipped with optical network termination device with one optical port. So let's start with this one. And as if it is a fixed network, we will try to just follow connectivity. And this is it. That's all work necessary to do it, because this is FTTH network. Fibers are connected to splitters. Only the last drop was not connected, so we had to choose this element. And now just by clicking follow connectivity, we have the whole route established. So now we will have to finish our work and save the issue. Now if we select the same underground route in PRM data tab, we will see another customer here, Toronto 15 customer, which is planned, and on our target device information we will also see another device connected to fibers going through this underground route section. So this is how PRM supports WDM devices and passive optical networks. Once fibers are connected, the routing can be automated. If optical devices are already in place and fibers or cables are connected to them, assisted manual routing is very straightforward, and as you have seen, pretty convenient for PNI and PRM users. I would like to present you how PRM integrates with Optical Network Atlas. ONA is a very convenient tool to generate optical network schematics. It works for traditional fiber networks and for passive optical networks as well. ONA integrates with PRM in two ways. The first feature is that ONA can generate schematics for splices when PRM has its planned connectivity. So every time when you plan to create new connectivity, to change connectivity in a splice, ONA can generate a schematic for this splice to present how connectivity has to be changed. The second feature in this integration between two products is that ONA can generate a schematic for the whole PRM route and provide convenient information and documentation for field workers to instruct them how to change the network in order to establish this PRM issue, the route in Fibre network. So let's take a look how it looks in our application. Let's get back to our demonstration PRM, which we have created at the very beginning of this demonstration. It has been created by hand, and as you remember, later using auto routing, we have found much shorter path for this route. This route has a lot of non-existing connectivity. So you can see it here. Many connections do not exist, and they will be created once this PRM issue will be activated. They all can be seen, this non-existing connectivity can be seen also by looking at these red dotted lines here. So let's select this splice and create ONA scheme for this splice. It will take several seconds. And now here on this ONA tab, you can see the schematic for this splice, how this splice looks currently. So without any changes in connectivity, how fibers and the group of fibers are connected. You can see the other end of each fiber or group of fibers. You can see cable name, the location this cable leads to. This is another cable, and when connectivity exists between fibers or group of fibers, they are connected inside this splice box. And here you can see how this splice should be modified in order to establish this issue. You can see that everything is almost the same, apart from this distinguished with purple color line, which shows how fibers has to be connected in order to create this demonstration PRM issue. So this number here relates to this number which describes this line in the schematic. So this is the first feature, how ONA integrates with PRM, and the second one allows us to create a full schematic for PRM, for physical route, made by Physical Route Manager. So let's create a schematic for the whole demonstration PRM route. We start a wizard for ONA schematic generation and just give a name for the route we want to generate schematic for. And now we have to wait several minutes. Okay, this schematic has been generated in about 1 minute. So you can see here at the first two pages of this schematic present the whole top level overview of this route. So you can see the same information as in PRM. So which locations and splices are on this issue route, on the path on the fiber path of this route. So then you can visit each splice and each location and see the same information as you have seen before. So let's take a look at this splice. You can see how fibers have to be connected. This is the same information as before. You can see all fibers which are consumed by this PRM. They are presented in different color here, fibers 3 and 4 in these two cables. The same here. So this integration allows to generate very comprehensive documentation for each fiber optic element on PRM route. You can hand this documentation to field workers, you can print it and send it to your customer in order to show how much work has to be made in order to establish this particular service. Thank you very much. I hope this presentation has been useful for you. Thanks.